Assalamu alaikum warahmatullahi wabarakatuh, students and everyone. My name is Mohammed Ahmed Zeb Kamar, and today I will be teaching you the topic dual simplex methods. In this topic, we will be first discussing that what is dual simplex method and how do we use it with example. So without further wasting time, let's dive in. So first we will discuss what is dual simplex method. Dual simplex method is a simplex method type which is used in solving linear programming problems which are always of minimization type, and minimization representation is given by the less than and equal to sign in its constraints. The constraints having less than and equal to sign. And it is also given that the objective function which will be discussed in this slide will be also should be of minimization. If it is of maximization, we will further see into it. But for now, do remember that the objective function should be of minimization type. And the constraints should be having less than and equal to sign. Let's start with an example like this given over here. It is written that a person wants to decide the constituents of a diet to fulfill his daily requirements of protein, carbohydrates, and minimum cost. The word minimum indicates that the problem is of dual simplex method type and minimization objective function will be given here. So there are four different types of foods, each of them doing their different types of amount of protein, fats, and carbohydrates, and cost per unit in rupees, and their minimum requirements are also given. So first we will start by creating the linear programming model, which is a basic step before solving any type of method, whether it will be a simplex method, a graphical method, or dual simplex. Since this is a dual simplex method, the objective function is formed by the cost per unit in rupees, and this is given in the form of minimization function. After that, these are the constraints which are in the form of subjective, and these are the constraints which are given by 3x1 plus 4x2 plus 8x3 plus 6x4 is greater than or equal to 800, 2x1 plus 2x2 plus 7x3 plus 5x4 is greater than or equal to 200, 6x1 plus 4x2 plus 7x3 plus 4x4 is greater than or equal to 700. All of these constraints are maximization type, it is given, but we need to convert them into minimization type. So we need to change their signs, and the non-negativities will not be changed as their constant, that all variables should be greater than and equal to 0, otherwise it is impossible to solve it. So in case of minimization, there will be no changes for both the constraint and objective, but in case if any of them, as given here that the constraints all of them are of maximization type, we will convert them into minimization by multiplying both sides by -1, which will result in changing the sign and the sign from greater than equal to less than equal to, as shown over here. After this conversion, we will introduce variables called the slack variables. Now over here, slack variables are the type of variables which are used in further solving for the dual simplex method, and they are given dependent on the number of times each variable is repeated. For example, x1, x2, x3, and x4 are repeated 3 times, so 3 slack variables will be inserted into it. In first equation s1, in second equation s2, and in third equation s3. And after we have done implementing the slack variables, we shift all the variables of objective function on the left hand side, resulting in 0 on the right hand side. So as you can see over here that all three values with coefficients on right hand side, we switch in on the left hand side, which results in this. After this, we will construct a representation table which will give the values of the equation, and then we will perform more methods. The table consists of headings, basic coefficients, x1, x2, x3, x4, and the slack variables along with the right hand side. So the values of the objective function, the slack variables are given as they are shown here. For the slack variables, they are given in these formations, and for the right hand side column, these are the four values for both the objective function and the constraints. After this, we will now start the dual simplex method by first selecting the most negative value from the right hand side. So as you can see from the right hand side, out of these four numbers, which is the most negative, it is 800 over here. So we'll select 800 and mark that row in which 800 is located as key row, which is given in blue color. After this, we will divide all of the variables of the objective function with the key row. The key row is this row in which minus 800 and all the other numbers are highlighted in blue. After we have divided them, our ratio row will be started to fill. So here you can see that we have divided the z variables with the key row variables, which will be giving these numbers in the ratio row. Minus 45 divided by minus 315, 40 divided by 40 is 10, minus 85 divided by 8 is 10.6, minus 64 divided by 6 is 10.6, and so on. After this, after we have performed the division, we will now select the least ratio element from the ratio row. So in the ratio row, you will see that 10 is the most least element, which is the most less one. So we'll highlight 10 and the column in which 10 is located. Now we see that when the key row and key column intersect, the intersection point in which a number will be intersected is the key number. You see over here with the one with the exact sign, that is the key number, which is -4. So now we will perform some methods into it. As you can see over here, we have applied draw echelon method. So actually draw echelon method is from linear algebra course of chapter matrices, in which we have performed Gaussian elimination. In Gaussian elimination, it is said that the matrices will have leading 1 as the starting variables, and all of the variables above and below the leading 1 will all be 0. So we will be performing Gaussian elimination on the key number by dividing the number with itself, making it the leading 1 number. And now we will convert all of the numbers above and below 1 into 0 by using Gaussian elimination. So we have given the identification of each row. Objective function is row 1, S1 variable is row 2, S2 as row 3, and S3 as row 4. Over here you can see that in the red color, identification 1 is the leading one. So we'll convert all the values above and below in the form of 0. After we have performed, you will see that all of the values have been converted into 0, and along with all of the variables for row and columns and the right hand side have also been changed. After this, we will again apply step 1 to see if there are any more negative values in the right hand side. So in the right hand side, there are no more negative values. That means our process ends here. If this was negative 8,000 or negative 200, we had then again applied the steps from 1 to 10. But over here, the step is finished. There are no more negative values. After that, we will determine the value of the objective function z and other variables. So you can also see over here that instead of slacking variable 1, I have put it S2, is because the point at which both the key row and key column intersected is in this row S1, which will now be changed into X2. So over here you will now see that we have obtained the values for z and x2. X1, x3, and x4 have not been found because they were because the process has stopped till here. And as you can see, we have also determined the values for z and x2. For objective function z, the value is 8000 and for x2 is 200. And after we have done this, we will also put them into the objective function equation. Over here you'll see, and after you put in the value of z and x2, you'll see that it will result in 0. I hope you guys have liked this, have found this chapter useful. Thank you for watching. Take care and goodbye.